Thank you for being here today. I am Engineer Kashif today to talk to you about ideal and actual Brayton cycle with operation characteristics. Now, I want to move the operation of Brayton cycle in next animation pictures. It's continuously run into the compressor where it is compressed to a high pressure. The air then enter a combustion chamber where it is mixed with the fuel and combustion occur, resulting to combustion product at an elevated temperature. The combustion product do work by expanding through the turbine and are subsequently discharged to the surroundings. Part of the turbine work developed is used to drive the compressor. An air standard study analysis is used to study the open gas turbine engine with the assumptions that air is the working ideal gas and the energy generated by the combustion is accomplished by a heat transfer source. Ambient air enter the compressor at state 1. And later return to the surrounding at state 4. With a temperature higher than the ambient temperature. The discharged air would eventually return to the same state as the air entering the compressor, so we can consider the air passing through the gas turbine engine as undergoing a thermodynamic cycle. The air standard Brayton cycle represents the state visited by the gas turbine with an additional heat exchangers for the air is released heat to the surrounding and return to its original state 1. The air standard Brayton cycle consists of two heat exchangers, compressor and turbine. In ideal air standard Brayton cycle, there are no frictional pressure drop. There are no frictional pressure drop and the air flow at a constant pressure through the heat exchangers. The process through the turbine and compressor are assumed to be asentropic. In Brayton cycle, efficiency, overall work done divided by heat introduced to the combustion chambers. Overall work done is equal to mechanical output at turbine W1 and W2 mechanical work input to the compressor by the shaft, which is coupled turbine and generator. In TS diagram, there are two asentropic process and two are constant pressure process. So temperature 0.1 to 2, 2 to 3, and 3 to 4, 4 to 5. And an ideal Brayton cycle, entropy at 0.1 and 4 are constant and entropy at point 3 and 4 are constants. So it means that there is no losses, there is no irreversibilities. Now I want to move the actual Brayton cycle. You can see this is the deviation lines, this one and this one. Actual Brayton cycles differ from the ideal cycle in all the four processes. The compression process and expansion process are non-asentropic. These lines are also in actual cycle will be deviate. Pressure drop during heat addition and heat rejection. The pressure of irreversibilities causes these deviation lines. As a result of non-asentropic compression and expansion, the compressor need more work than the ideal cycle and turbine generate less work. Asentropic efficiencies reflect the amount of deviation of the total actual compression expansion process from the ideal. Total pressure losses in the heat addition rejection process also need to be considered. In next lecture, we will discuss the combined cycles. This will be combined cycle. Combined cycle means that Rankine and Brayton cycles both are used in these cycles. Simply you can see this is the combined cycles. We will discuss in next lecture. So thank you.